Okay, so we're ready to start our very last lecture. This will be on chapter 10, air conditioning systems and heat pumps. Sorry about the video noise again. So this, like I said, this will be the last lecture. And then I've got one more video to do, and that's on strictly solving problems. And the problems I'm going to solve are the problems like is on the homework, and also it's the problems like you're going to have on the final exam. So let's get started with chapter 10. Chapter 10, we're talking about, again, air conditioning, refrigeration, heat pump systems. When I did my bachelor's degree in mechanical engineering long ago at Mississippi State, I not only took a couple of courses in thermodynamics, also took 6 hours of refrigeration and air conditioning. So I know the subject matter reasonably well, and I've used it in the practice as an engineering manager at Eaton. So hopefully I'll be able to explain it. Don't say I don't know everything. There's plenty I don't know. But let's get started. So let's pull up a screen. Slides. Hold on. We'll get there. There we go. Maybe make it a little bit larger. Now I need to be sure and join. Hold on. I'll get it started in a second where I can share the screen. Okay, so we're off. I'm going to hide myself down here, maybe out of the way. Put the slides over here. Now we will be pretty much just going by the slides. I'll try to throw in a few comments along the way that may make it interesting, but this is chapter 10. It's not the complete chapter 10, but it's the part that you will be responsible for, and it covers the basics. So chapter 10, refrigeration and heat pump system. By the way, when we say refrigeration, we not only mean like real cold cooling like is in a refrigerator or a freezer, we also mean air conditioning like is in your home or in the building and so forth. Air conditioning is just use the exact same circuit as refrigeration. It's just not quite as cold. And heat pumps, as we'll see, use the exact same circuit as air conditioning and refrigeration. So make this just a little larger. All right. So the learning outcomes here is to, and I'm sorry, I'm going to be reading to you a good bit, but I want you to learn how to analyze a refrigeration or a air conditioning system. Also how to analyze a heat pump, how to make the calculations, how to draw the TS diagram, and from the TS diagram and you're given conditions at the different states to be able to look up the enthalpies. Generally, there'll be only one enthalpy that you'll have to calculate or interpolate, and that's as you've seen before on your test 3 and on homework, that's determined in H2 and H2S. I won't go into that in this presentation, but I certainly will when I do the problem solving video next. So actually these systems, air conditioning systems, it's called a vapor compression cycle because it's a two-phase situation, and you do use both states. It's a two-state process. You'll use a liquid and vapor phase. So there will be a dome to contend with. But sorry about getting my tongue crossed up. Let's see if we can get started here. So this is a schematic of a typical air conditioning or vapor, they call it vapor compression refrigeration cycle. It has 4 components. Every one has 4. The evaporator and an air conditioning and refrigeration, that's where the cooling is done. That's what does the cooling. We have to have a compressor. We have a condenser and an expansion valve. And so that's, now we're going to abide by what this diagram says. It's a little different than I've taught you so far. And I'm going to try to make sure it does not confuse you. But the energy transfers we're going to take as positive in the directions of the arrows. Now this is different, I understand, but I think we'll be fine. So in this refrigeration cycle, it shows work into the compressor and it shows it positive going in. So we'll use that. Q coming out of the condenser shows positive coming out, and Q going to the evaporator shows positive coming in. I don't like to do it like that, but that's the way the book does. And again, I don't think you're going to be confused. I'm going to try to make sure you're not. But there's the 4 components. When this system is running, well, actually what you're doing in a refrigeration system, you're taking, you're sort of sucking up the cold, the heat from an area, and you're storing that heat in the evaporator, in the vapor in the evaporator. And then you go through a compressor and you're compressing it up and you increase the pressure and the temperature, as always. But this time it's good you increase the temperature because now you've got hot, high pressure and you can get rid of the heat through the condenser. So the process sort of goes like this. Pull in the heat in the evaporator, go through the compressor, compress it up to higher pressure and higher temperature, discharge the heat from the thermodynamic fluid, from the refrigerant in the condenser, and go through the expansion valve and continuously go through the process over and over. So yeah, this is what I meant to say. I lost my train of thought a little bit. What you're actually doing is taking heat transfer out of a cooler area and transferring heat to a hotter area, which we know violates the second law if you try to do that without any work input. But the compressor allows you to do that because here you go through you come into the evaporator as a mixture, about 30% vapor and 70% liquid. You go through the evaporator, and during the evaporation process, it changes state from a mixture to 100% vapor, saturated vapor. And in the process, it pulls in a lot of heat. It's just like if you rub some water on your wrist and you go outside and the humidity is low, you can feel the coolness of that water evaporating. That's the way the evaporator works. Okay, it comes out of the evaporator is a saturated vapor. Compressors don't compress liquid, so it goes through the compressor. Compressor bumps it up by a factor of, I don't know, 6 or 8. And when it comes out of the compressor, it's still all vapor, superheated vapor now, and it's hot. High pressure goes through the condenser, gets rid of all that heat it collected here and collected here, and then goes through an expansion device and starts all over again. So I pretty much mentioned this process 4-to-1 through the evaporator. 2-phase liquid vapor mixture refrigerant is evaporated through heat transfer from the refrigerated or the cool space. It sucks in heat, the evaporator does. Comes out as a saturated vapor. Process 1 to 2 is the compression. Vapor, all vapor refrigerant is compressed to a relatively high pressure and temperature. requiring work input. So you have to put some work into the compressor. Process 2 to 3, vapor refrigerant. It's a hot, high pressure vapor goes through the condenser, and it comes out of the condenser as condensed liquid, a saturated liquid. The vapor refrigerant condenses to liquid through heat transfer to the cooler surroundings. Now, in an air conditioning unit, the cooler surroundings out here might be 100 degrees Fahrenheit, or say 90 degrees Fahrenheit. So that means you have to get this condenser pressure such that the temperature in the condenser is higher than the temperature outside, else you can't get any heat transfer. We'll talk about that later. Process 3 to 4 is a throttling process, constant enthalpy process, where you go from a high pressure liquid to a low pressure mixture, part vapor, part liquid. So when we analyze the vapor compression cycle, we analyze it just like before. Each component is analyzed as a control volume at steady state. Dry compression is presumed. That means it's all vapor. There's no liquid in the compression process. An ideal process, the compressor operates adiabatically, meaning there's no irreversibilities. It's isentropic, adiabatic, and reversible. The refrigerant expanded through the valve undergoes the throttling process. That's this valve we show here, the throttling process. And we neglect kinetic and potential energy changes. Now, when we go through the evaporator, we apply the first law and we find the heat transfer per pound of refrigerant is H1 minus H4. And Qn is referred to as the refrigeration capacity, or the amount of cooling or amount of refrigeration. It's expressed in kilowatts in the metric system, BTUs per hour in the English system. By the way, a common terminology used in the air conditioning refrigeration business, or in those type industries, is the ton of refrigeration. Now, it doesn't mean 2,000 pounds or anything like that. I don't know where the ton originated, but a ton of refrigeration equals to 200 BTUs per minute, which is 12,000 BTUs per hour. And that ends up being about numerically equal, BTUs per minute are about numerically equal to kilojoules per minute. That's interesting. Now, a ton of refrigeration, if any of you had an HVAC man come out and look at your unit or talk about your unit, he's going to probably tell you got a 2-ton unit, 3-ton unit, or a 4-ton unit. That's the cooling capacity. My home has 2 units, air conditioning units. It has a 4-ton unit for the main floor, and that's 48,000 BTUs per hour, or 4 times 200, or 800 BTUs per minute. That's a reasonably good size for a residence. Then my upstairs is a 2-ton unit. So that means it has the capacity to cool at its rated conditions 2 tons, which is 400 BTUs per minute, or 2 times 12,000 BTUs per hour, or 24,000 BTUs per hour. And so that's what the QN is. In the metric system, it would be kilowatts. So let's see, 1 ton would be about what? 0.2, let's see, 0.2 kilowatts per minute. 0.2 kilowatts per minute. So what is 60 times that? 200 kilojoules per minute, that's 0.2 of a kilowatt per minute. Anyway, We'll figure it out. My brain's not working too good. I need another sip of coffee. So if we use work, error showing work input is positive. By the way, on the final exam, I'll give you these formulas and I'll make sure you don't get positive and negative, that it doesn't trip you up. And if it does, and you get a negative or when it should be a positive, I probably won't even count off, because I realize that it's somewhat disconcerting for me to teach all the way using the sense of heat and work that we covered in the first few chapters, which I think is the right way to do it. But the book in later chapters, it throws all of that away sort of, and start using the arrows as plus, as the sense of plus. But we're not going to let that trip us up. All right, now if we look at the compressor, these are, let's go back to the circuit. All right. For the heat transfer in, the cooling capacity, it's m dot, the mass flow of the refrigerant, times, we want it to be this is a positive number, so it's Q1 minus Q4. Let's see if that's what he's doing. Yeah, I mean H1 minus H4, sorry. M dot, now the same M dot, of course, flows all M dot times H1 minus H4. Now, going in the compressor, if we want to use plus as work going in, because that's the error shows, we know that state 2 is a higher energy state because it's compressed up to higher temperature and higher pressure. So the work for the compressor to jive with the arrow is M dot times H2 minus H1. And again, I'll have these written down for you. So that's the work of the compressor. And by the way, that's H1 minus, no, I'm sorry, H2S minus H1 is the adiabatic work, isentropic work, and I don't know if I said that, H2S minus H1 is adiabatic work, and H2 minus H1 is the actual work. So we got to deal with that H2S and H1 again, and I'm going to teach you how to make those calculations and not sleep. I hope so. I'm not going to do here. I'm going to do when I do the problem solving video. Now we go to the heat out of the condenser, the heat rejected, but which, by the way, is the heat pulled in here plus the heat injected here during the compression process. So let's look at this. Air, we want it going out positive. So we want to get a positive. We want to go with the arrow. So the higher energy state is H2. So it's going to be M dot, Q out is going to be M dot times H2 minus H3. And then the expansion through the throttle valve is a constant enthalpy process. It goes from a saturated liquid at high pressure to a two-phase liquid vapor mixture at the pressure of the evaporator. By the way, when you design in this system, let's say I want to use it in a household as an air conditioner. Well, I want this coil, evaporator coil, to be somewhere around, in degrees Fahrenheit, probably around 50, 60 degrees Fahrenheit. So if I'm designing it, I'll look at my tables and I'll choose a pressure that gives me that temperature. Let's look at the tables. All right, let's go to the English units. So we're going to deal with R134A. Let's look at page 994. So if I want to design a HVAC system to give me about a 60-degree coil temperature, what pressure did I choose? All right, well, let's look down here. Here's about 60 degrees. So I would choose a evaporator pressure of about, from 60, 70, 80, probably 70 pounds per square inch. That would give me the 58 or 59, around 60 degrees. Now let's look at where I would want the higher pressure to be. All right, so let's say I'm in a Mississippi hot day and we've got 95 degrees Fahrenheit outside. Well, I'd want my coil to be, and say that's the design point. Well, I'd want my condenser coil to be hotter than that to be able to get rid of this heat. Of course, you know there's fans blowing all through the evaporator, throughout your conditioned space, and there's the big fan set. By the way, the condenser and the compressor are the units that's sitting outside of your home in the cabinet, or you might call it the rectangular enclosure outside. It has the condenser and the compressor and maybe the expansion valve, not sure. But inside your house, you would have the evaporator. And of course, they're fans that distribute air over the condenser and evaporator, different fans to aid in the heat transfer. Now let's go back to the condenser. 95 degrees outside, so we want to have a condenser temperature of at least probably 10 degrees above that. So let's say 105. Let's say 100, all right, 105. Let's go over here and see what kind of pressure we'd need to compress that refrigerant up to. So we want to get about 105. So looks like we might be about 150 PSI. That would give us a temperature in that coil of about 110, 160 would be good. I'd give you 110 degrees. So that's how, oh, I don't know if I don't know if I messed up. Am I still recording? Yeah, I'm still recording. Sorry about that. Have to fast forward. Okay, I want to share the screen. Make sure you had that. Yeah. Okay, you were seeing that. All right. Okay, let's go back to just the slide, put the slides from. Now, I've explained a lot of these upcoming slides. So there's Q, there's a heat transfer per pound of refrigerant, H1 minus H4. There's a compressor work per pound of refrigerant, of circulating thermodynamic material, H2 minus H1, condenser, H2 minus H3, and expansion valve, H3 is equal to H4. As you see, these refrigeration systems are pretty darn simple. Oh, there's a couple of parameters we want to look at. Coefficient of performance, we talked about that. That's beta. And beta is equal to the QN, the refrigerate, QC we called it in some of the other diagrams. The amount of cooling you're sucking in or absorbing divided by the work of your compressor. So beta is H1 minus H4 over H2 minus H1. And it's always going to be greater than 1, by the way. The way to interpret that is beta, say beta is 4, calculates out 4. That means you're getting 4 units of cooling for every light unit of work. You're getting 4 BTUs for every watt. Okay, you're getting 4 BTUs for every watt of electricity. Or you're getting, well, yeah, it's units of refrigeration per units of work. And I mentioned that SEER ratio, seasonal energy efficiency ratio, SEER. That's what you see air conditioners rated as. SEER takes the COP, which is dimensionless because it can be watts of cooling per watts of electricity. So COP is dimensionless. So what you want to end up with is a beta tight ratio, but the definition of SEER is BTUs per hour on the top. So that's BTUs per hour on the top per watt of input power on the bottom. And their conversion factors, you can convert that. Now, just as before, we have a maximum beta that depends on the Carnot criteria, the second law of thermo, and that's TC, the cold temperature. That would be like your conditioned space, maybe 70 degrees, 75. TH is the outside, like the 95 degrees, and then TH minus TC. This TC has to be an absolute. Degrees ranking in the English system, degrees, no, Kelvin in the metric. Now this is a difference here, so it can be either in degrees C, degrees F, or whatever you need. So as we know, the Carnot coefficient of performance, or beta max, represents the best you can do between the two temperatures. And as you guys know by now, the real systems very seldom get anywhere close to the theoretical maximum. Now here's the TS diagram. So now what's not shown here, and you'll have to use your imagination a little bit. I couldn't find a figure that had it. This shows the compression process through the compressor, the isentropic process, from 1 to 2S. Where state 2 has the same entropy as state 1, but at a higher pressure. The actual compression process we know goes sort of like right up here and intersects this same pressure line. Now again, this is the low pressure line, and they've got 0 degrees C. So that's the temperature, but through here, temperature and pressure are the same. Let's look up and see what the pressure is at 0 degrees C. So we'll need to go back to our, metric tables. Let's go to, let's go to 925. All right, close enough. All right, let's look at R134A. Let's look at the temperature table. That's on page 943. So let's go to 943. We want to look at this. Whoops, 943. 943. So what did he say? 0 degrees C. All right, let's find 0 degrees C. Here we are right here. So our low side pressure to give us 0 degrees C would be about 3 bars. All right. So if we designed our system to give us a pressure of 3 bars, but by the physics of the refrigerant, we would get 0 degrees, or about 0 degrees C. Now let's look at 26 degrees C. Okay, what is that in Fahrenheit? I still think in Fahrenheit. What's 26 times 1.8? That's 160, that's 1.8. 26 plus, no, about, hey, I got a calculator here. My mind's not working too good. I usually do that in my head, but I'm not having a good day. 26 degrees, 1.8 times 32 plus. That's only 80 degrees. It's not very high temperature. Let me run that again. 26, 1.8 times 32 plus. Yeah, 79 degrees Fahrenheit. That's not really a very high temperature. You must be in a cool area. But anyway, you see, so 26 degrees C, what pressure would that give me? Let's go over here at the table. About 7 bar. So at 0 degrees C, we're about 3 bar. At 26 degrees, we're about 7 bar. So about 3 bar to 7 bar in round numbers. Now, when you're designing a system like this, you don't want to go excessive. That is, you don't want to go, if you're living In Mississippi, you would want to design for like 90, well, probably any air conditioning system. Frankly, I don't like that 20 degrees C. This may be a heat pump schematic. Let's look at what a temperature, let's say 95 degrees C outside, 95 degrees F, 95, enter, 32 minus 1.8 divided by, that's 35 degrees, not 35 degrees C. Now let's look back at our table. 35 degrees C, you're talking about 9 bar. So in Mississippi, you would have to go to about 3 bar. In fact, that 0 degrees C is a little bit too low. This is like a refrigerator here. Let's do some Mississippi numbers. So let's go to 40 degrees F. 40 degrees F on the low side, that'd be 1.8 divided by, that'd be about 4 degrees C. So that'd be about 2.5 bar. You would want to set your lower pressure 2.5 bar. Now, what we say, 95 degrees, I forgot, 95, enter, 32 minus 1.8 divided by 35 degrees C. So we're about 9 bar. So what did I say? I can't remember anyway. I need to write this down. But anyway, we'd go up to about 2 bar or so, up to 9 bar. Maybe, no, we'd go about 3.5 bar up to 9 bar. But here's the point I'm trying to make. You don't want to go excessive. Oh, it would make it easier on the equipment to heat transfer if you went way up in the temperature of the condenser to make the heat transfer away, rejected to the outside easy for the system to do. To go make this evaporator cold as possible. You don't want to get below 32, you'd have ice forming on your coils, 32F. But that would make it easier to cool the space. But the problem is, the further these two lines are apart, the high pressure and the low pressure, the harder your compressor has to work. And it's really sensitive. Your COP is really sensitive to the space between the low temperature and the high temperature. The pressure between the low temperature and the high temperature, that's your compressor work. So you tend to want to keep that as small a gap between the low pressure and the high pressure as possible to give you the best performance for your design. Now, I don't like the way he drew this figure. He shows, this is good. Let's get away from those dots. This is good. I don't like those dots. They don't do any good, do they? They just cloud the issue. All right, let's put it up here. That's all right. Well, I got these. Put those back in the right place. Okay. This point is when we deal with the ideal refrigeration cycle or air, this point is right here on the saturated liquid line. Where it is now, if you weren't given that point, it'd be hard to look it up. You'd have to know some other information about that point. Whereas with the cycle we'll deal with, we'll call this the saturated liquid line right here. And we can look up that. We just have to know this pressure here or temperature and look up the HF, and we got it. And not only that, when we look up this HF here, that's H3 and it's also H4. But then when we get to state H4, we got to calculate the quality. Well, maybe not. Depends on what the statement of the problem. And then this position, this going in the compressor, it shows it slightly out in the superheated range. Normally, it would be right on this line here as saturated vapor. In other words, we go to the tables at this pressure or temperature and get Hg. Then the compression process, like before, adiabatic, isentropic, S1 is equal to S2, constant entropy. And then the actual process increases entropy. And to be able to calculate state 2 and state 2s, if we were given, normally you're given this pressure, so you know this entropy here, so you look in your mini pressure table, the mini table for whatever pressure you're dealing with out in the superheated area, and you'll have to interpolate for H2S. And if you know H2S, now you interpolate for H2S, you know H1. If you're given the isentropic efficiency, you can calculate H2. Or vice versa, if you're given H2 and can interpolate for H2S, you can calculate the adiabatic isentropic efficiency. But you have to be given one or the other. And what the point of, I think what the point of this, this curve is, because of irreversibilities, you do have this increase in entropy, and you do have this temperature 3 tending to go out a little bit on this line, and you tend to have the vapor not being saturated vapor, but slightly superheated. But we won't worry about that. I'm going to skip through this. Isentropic compressor efficiency. Well, he likes to use negative work of the control valve isentropically for the negative actual work of the control volume, not control valve. And our control volume is now the compressor. By the way, when we draw a control volume of a compressor, not only do we show the input and output and the conditions at those 2 points, we also show the shaft being spun up with an arrow to show that there's shaft work. I think all of you missed that on the test 3, but I know you'll all get it on the final. So we could have, like I was saying, if I use the sense of heat transfer and work, what's positive, what's negative, like we were taught at the first of the course, I would have H1 minus H2S over H1 minus H2 equal the compressor. It doesn't matter. As long as you flip the 2 and 1 on the top numerator and the denominator, it doesn't matter. Now he wants these to be both positives as the arrow going into the compressor. So he's got H2S over H1, H2 over H1. Now you have to I always have to think. Yeah, well, I don't like to depend on the formula. I like to write it out. So I like to think it out. Which one of these is the numerator and which one is the denominator without looking at a formula? Well, I know I'm dealing with a compressor. And the isentropic work, the theoretical work, is going to be less than the actual work I have to put into it. So I know the isentropic number is smaller, so it goes in the numerator. Excuse me. The actual work is larger, so it has to go in the denominator. Here's a problem he works out, and he's got all the enthalpies already picked off. Now, as you know from working your homework and test problem, the real challenge you have is to come up with all those entropies. Now, they're really easy for a refrigeration and air conditioning circuit, but he's got them here and he goes through the calculation. He just picks them out of air. Here's H2S 272, H2 is 280, but he goes through and makes the calculations. The compressor work, also he has the M dot of 0.08 kilograms per second. These are all reasonable numbers. These are R134 numbers, but you wouldn't be able to look them up yourself in the table because you don't know enough about this point. If it were right here, you could look it up. This point you could look up, but this point you really can't find. Okay, so he's got all of this. He's got the refrigerant mass flow rate, 0.08 kilogram per second. And this would be typically what you'd have to do. But like I said, it's easy once you get all the enthalpies figured out. But he wants a compressor horsepower in kilowatts, the refrigeration capacity in tons. Remember, 1 ton in the metric system is 211 kilojoules per second. He might not use that type of conversion though. The COP, the beta, and the isentropic compressor efficiency, which is equal to H1 minus H2S over H1 minus H2. So let's just go through this real quick. The compressor power is just m dot times H2 minus H1, 0.08 kilograms per second. You know that enthalpy is kilojoules per kilogram. And you know 1 kilowatt is by definition a kilojoule per second. So the isentropic compressor power is 3.1 kilowatts. And I'd ask you for one more digit because I won't, unless that comes out 3.10, I don't know. Now the refrigeration capacity, that's the refrigeration going from state 1 to state 4. So that's going to be the same m dot times H1 minus H4. H1's a higher energy state, H4 the lower, and so you get 3.41 tons. Now he has kilojoules per second times kilojoules per kilogram. That gives kilowatts. Well, you want kilojoules here. Okay, so you stay with kilojoules. Kilograms cancel out, you end up with kilojoules per second. And we want to get into minutes, so we have to get 60 seconds per minute and use that conversion factor we just saw a slide or two ago. 211 kilojoules per minute is a ton. You get 3.41 tons. So that's a reasonably good size air conditioning system. And then you get the coefficient of performance. And again, you're using actual entropies here, not any H1, not any H2S involved. It's the real thing. So H1 minus H4, that's QC, or that's the refrigeration capacity. H2 minus H1, that's the work of the compressor. Put those in, you get 3.86, which is a decent COP. Now that is in dimensionless units. If I wanted to get the SEER of this air conditioning unit, I would start with the COP of 3.86 because that's BTUs out per BTUs. That's BTUs of cooling per BTUs of electricity, which you don't normally state electricity in BTU, or it's watts of cooling, which is traditional, or watts of input power, which is very appropriate. You got 3.86. So there's actually a conversion factor. What you want to end up in the SEER is BTUs per hour of cooling. So that'd be the units of the numerator, units of the numerator, BTUs per hour. The units of the denominator, you want watts. So that's how many BTUs of hour of cooling you get for each watt. And as it turns out, there's a conversion factor. I believe it's like 3.3413 kilowatts is a BTU per hour, something like that. But it's easy to figure. And that would end up being about a 13 or so SEER, which is pretty good. Now the isentropic compressor efficiency is defined as H2S. Well, I've defined it as you see in the formulas I gave you for a compressor is H1 minus H2S over H1 minus H2. He likes to do the negative of it and make both of these positive numbers here. That's fine. By the way, this little S here means isentropic. My notation is WCS is isentropic work. WCA is actual work. But anyway, whether you have H2S minus H1 over H2 minus H1, or H1 minus H2S, or H1 minus H2, which is actually the more appropriate way to have it, you're going to get the same thing. And since he gave you H2S and H2, it's just plug and chug to get the isentropic compressor compressor efficiency of 80%. That's about a reasonable number. Refrigerant selection, that's not so much of a design choice now. If you're dealing with an automobile, it's R134A. If you're dealing with a refrigerator or a freezing unit, it's R134A. If you're dealing with a commercial or a residential cooling unit, it's R410. Is it R460? I think it's R410A. We haven't done anything with R410A. I don't know why it's not in our textbook, the tables, but it's not. So just a little bit about environmental impact. About 10 or 15 years ago, refrigerants, the top refrigerant were either R22 or R12. Now the R, as you know, is for refrigerant. These were trade name Freons. Freon was a DuPont trade name. Freon 22 was R22. Freon 12 was R12. They had this nasty characteristic of depleting the ozone area. I'm not an expert in this field, but I do know that these refrigerants, once a sealed refrigerant system was broken into during a repair process, this refrigerant will just evaporate. It'll just disappear in the environment. But it goes up into the ozone layer and combines with some of the particles up there, and it ends up blocking, it ends up depleting the ozone layer. And the ozone layer is what protects us from ultraviolet rays of the sun. So it was doing some really bad stuff. But over the last 10 or 15 years, the refrigerant manufacturers have gone to R134A. Cars used to be R12, now they are R134A. Residential and commercial used to be R22, now they're R410A. And those newer refrigerants are much, much less, do much, much less damage to the atmosphere if they get free into the atmosphere. But now the environmental, every HVAC technician has to be certified that he understands how to evacuate a refrigeration system or a heat pump system or whatever and capture all of that refrigerant that's in there, not just let it boil out to the atmosphere and go way up in the ozone layer. So there's been a two-pronged solution to the environmental hazard of refrigerants. That's one, less polluting refrigerants and strict EPA regulations on how to deal with the refrigerants that you use. This just talks about the types of refrigerant. Yeah, there's the refrigerant used in residential and commercial systems, R10A, R134A. I don't know anything about this, R1234. Here's the old refrigerants, R12 and R22. These other refrigerants, I don't know, carbon dioxide, these, I don't know of any system that uses those. So anyway, there's a global warming, GWP, number associated with the refrigerants. You can see R134 is a lot lower than R12. Now, we're talking about global warming here, or we're not talking about ozone, but refrigerants unfortunately affect both the ozone and the global warming, or climate change, they call it now. Let's look at R410. It's 1924, and R22, well, that's interesting. It's 1760. I guess its ozone characteristics are much better, but looks like its climate change potential is a little higher. But anyway, R410A is what, R410 and R134A is what you deal with. Now it talks about different kinds of refrigerants, natural refrigerants. maybe they use somewhere, but I haven't run across a system with them in there. So I'm not even going to, I don't, they may be, they just haven't been commercialized to any extent. Now, the final, we've only got a few slides left. What do we end up? About 4 slides. Now we're going to talk about the heat pump. And again, it's very similar. I'm going to go back to sort of the front. Let's see. Yeah, let's look at this system. Okay. If I want to heat a house, then I move the condenser inside and use the same cycle. What happens is now the evaporator's outside in the cold weather, and I get this nice heat input from the compressor, and now the condenser, inputs hot air, and so you can use it to heat. But what you do, you actually, let's look at, you actually have, and physically, if you have a heat pump implies it can both cool and heat. With a heat pump, in the heating mode, okay, let's take the cooling mode. In the cooling mode, which show here, and the evaporator is inside the house, and it's providing some nice cool coils to blow air across. Now I want to heat. What do I do? Well, I don't physically go outside and bring the condenser inside and put the evaporator outside. What you do is you reverse the flow of the refrigerant. Now, instead of going, what is this, counterclockwise, it's going clockwise. And you do that with a switching valve. The compressor doesn't change rotations or anything, but a switching valve will now port the high pressure Freon through the coil that's inside. These coils are pretty much identical. So now the hot refrigerant is flowing through here and giving you heat, going through the expansion valve. Expansion valve doesn't care which way the refrigerant flows through it. It does its thing regardless. Now you go into the evaporator and you discharge out to the environment, the heat out to the environment. But what's nice about the heat pump, you're now using both the heat that you pulled in. Let me go to the heat pump. They draw it a little different here. I wish they had used the same circuit. They don't. All right, let's see if we can blow this up. Okay, so you have the same 4 components that you have in an air conditioning refrigeration system: compressor, evaporator, condenser, and expansion valve. But now, okay, now the flow of refrigerant is, well, in this way, it's still counter, it's clockwise, right? Okay, clockwise. So we go through an evaporator and it gets cold enough that it sucks in heat from the outside. And the outside's already cold, but this has to be colder to get heat in here to evaporate this refrigerant, because it has to enter the compressor as either a superheated vapor or a saturated vapor. We have work into the compressor now, so we increase both the pressure and the temperature coming out. This is all vapor going in, saturated vapor going in, superheated vapor coming out. Now we've got a hot, high pressure refrigerant that we run through the coil, that the condenser that's this time inside the area you're trying to heat. So now you've got nice hot air to heat your inside. And heat pumps are really efficient devices. The problem is if the outside temperature gets, say, and I mentioned this in class, gets say below 35 or 30 degrees Fahrenheit, it really gets hard to get these coils colder than that to suck in heat from the outside. One thing that happens is if you get below 32 degrees in these coils, you start forming ice on the coils. Now you can get around that by having the coils where the air can't get to them, but it's really hard. So the Achilles heel of a heat pump is they work great until the temperature gets, they're very efficient. You can get 4 or 5 units of heating for every unit of, you can get 4 or 5 watts of heating for every 1 watt you put in the compressor all day long until it gets cold, real cold outside, and then the heat pump starts being, sort of starts shutting down. It's not efficient at all. So you have to have resistance heating as a backup. And as you know, when you have resistance heating, for every watt of heating, you have to have a watt of electricity. So it's really inefficient. Resistance heating is as far as energy savings, but it's necessary when the temperature gets really cold. Fortunately, around here, heat pumps work pretty darn well because it generally doesn't get much below. We don't have a lot of freezing nights here where we'd have to invoke the resistance heating. So he's got a few items here. Got state 1, that's going into the evaporator. He's got an enthalpy of 244.1. Oh, no, I'm sorry. State 1 is saturated vapor coming into the compressor, 244.1. Again, we're dealing with R134A. Although for a house, you wouldn't be using R134A. You'd be using R410. And that's why I don't know why this book doesn't incorporate R410. But anyway, the principles are the exact same. It's just not going to do quite as good at these temperatures that you have in a residential situation. But anyway, the enthalpy, and again, the problem with analyzing this is to come up with the enthalpies based on the given information. That's your issue. He's put them right out here for you for this little example, so it doesn't really do you much good. But R1, H1 is 244.1. H2 coming out of the compressor is 272.0, not a tremendous amount of difference. And H3 is equal to H4. That's the the enthalpy coming out of the condenser, saturated liquid going through the expansion valve becomes this is a high pressure saturated liquid. It comes out as a lower pressure mixture, part liquid, part vapor. So he's got those values, and you can make these calculations then. That the compressor is M dot. Did he give you M dot? He had to. It was 0.86 kilograms per second. That's a very realistic number. So he calculates the work into the compressor is 2.4 kilowatts. The heat transfer to the building inside, again, he didn't give you, he gave you the enthalpies and the mass flow rate so you can calculate it. 15.4 kilowatts, that's reasonable for a residence. And now the gamma now becomes, instead of the QC, it's QH or Q out, which is the heat being dissipated inside your building. And he gets 6.4. That's a pretty good number. If we look at the maximum per the boundary temperatures, it could be 20. As you see, it's not anywhere close. And if you were looking for the SEER, S-E-E-R, I'm going to pull up that table. Conversion factors. Now I need to check and make sure you're seeing this. I'm just about done, by the way. Okay, you're seeing it. So we have this conversion factor here we can use directly. That a watt is 3.413 BTUs per hour, or a kilowatt is 3,413 BTUs per hour. Oops. So what am I looking for? So this COP, remember, is like units over like units. So you can interpret that as watts of heating over watts of electricity. I want to leave the numerator alone as watts, but I want to change this from 6.4 let's say, yeah, 6.4 watts times, am I getting this right? I want to multiply the numerator by 3.413, okay. So 3.4, that gives about 20, doesn't it? That's the SEER. And remember, the reason I bring that out is because if you ever find an air conditioner or heating unit, it's going to be rated by SEER and not gamma and beta. So it's 6.4 times that conversion factor of 3.4. That'd be about 20. That's getting pretty close to the. Oh no, I'm sorry. I'm talking about different things. SEER, it's very possible to run higher than this gamma max because it's a whole different thing. Gamma is like units over like units of heat over like units of electricity. SEER, S-E-E-R, is BTUs per one specific ratio, BTUs of hour of heat per watt of electricity. So that's it. So that we didn't work any problems here, but I'm going to do another video very soon where we just work problems. The problems will be similar to your homework problems. The problems will be similar to the final exam. Won't be the same numbers, of course, but if you're able to work the homework, you'll be able to work the final exam, and you'll end up with a good grade this test because, like I said, if you make a grade on the final exam higher than any of your test grades, I will substitute that final exam grade for both that test grade and your final exam. Okay, hope everybody has a good afternoon. Over and out.